For this video, we are going to solve a situation or problem related to engineering mechanics. Given are the details, figure, and two questions that we are going to solve as we go along in this video. For the first question, we are asked for the tension in ropes 1 and 2 in the figure given a value for alpha. To expose the two tension forces asked in this question, let us cut the rope, say in this part. From our situation, it was stated that the barge is pulled by these two tugboats. Hence, if we will reveal the two tension forces, it will look something like this. The green arrow is simply the tension force in rope 1, T1, and the blue arrow being the tension force in rope 2, T2. Since we have two forces, and the information for the resultant of these forces is given at our situation, we can apply the parallelogram law. That is, we can copy T1 and attach it to the tip of T2, and similarly, we can copy T2 and attach it to the tip of T1. And now, we have formed a parallelogram. From our situation, it was also stated that the resultant of these forces is directed along the axis of the barge. This is the axis of the barge. Therefore, this is the resultant R, emerging from the common point of T1 and T2. Notice that we have formed two triangles. Instead of analyzing the whole parallelogram, we can simplify our analysis by considering the bottom triangle, or specifically the bottom force triangle, with the pink side being the resultant R given as 5,000 pounds at our situation, the green side being T1, and the blue side being T2. Note that there are two angles given in the figure. First is the angle of T2 from the resultant being alpha, which is also given as 45 degrees from the question. Second is the angle of T1 from the resultant being 30 degrees. Since we know the angle of T1 from the resultant, therefore, this angle, which is still T1 from the resultant, would also be 30 degrees. Lastly, is this angle, which let's say is theta. We can solve for theta because we know that the angles 45 plus 30 plus theta is equal to 180 degrees, the sum of the angles of a triangle. Solving now for theta will give you a value equal to 105 degrees. At this point, we have an oblique triangle with values for its one side and three angles. Therefore, we can use the sine law. Take note that the A, B, and C's at the numerators are the sides of the triangle, and the A, B, and C's at the denominators are the opposite angles. If we will let small a as R, B as T1, and C as T2, by sine law, we will then have R, which is 5,000, over the sine of the opposite angle, 105, equals T1 over the sine of the opposite angle, 45, equals T2 over the sine of the opposite angle, 30. Solving first for T1, we can temporarily disregard the third term. From what's left, we can multiply sine 45 at both sides of the equation. Doing so will cancel the sine 45 at the right term where T1 is, which will leave us with T1 equals 5,000 times sine 45, which is the sine 45 I just multiplied at the left term and brought up at the numerator, over sine 105. Solving now for T1 will give you a value approximately equal to 3,660.25 pounds. And this is the tension in rope 1. Now, solving for T2, let us bring back the third term and temporarily disregard the second term. From what's left, we can multiply both sides of the equation by sine 30. Doing so will cancel the sine 30 at the right term where T2 is, which will leave us with T2 equals 5,000 times sine 30, which again is the sine 30 I just multiplied at the left term and brought up at the numerator, over sine 105. Solving now for T2 will give you a value approximately equal to 2,588.19 pounds. And this is the tension in rope 2. Therefore, these are the answers for the first question. Now, for the second or last question, we are asked for the value of alpha if the tension in rope 2 is minimum. If something will be minimized, a way to solve what is asked is by applying the principle of maxima and minima from calculus. Specifically, at this case, we need an equation for the tension in rope 2, which is T2, in terms of alpha, to minimize and solve for the value of alpha. To develop that equation, we can consider the same force triangle. But since the tension in rope 2, which is T2, will be minimized and we are solving for the value of alpha, therefore, the values we have solved in the first question for T2 and T1, including the value of alpha being 45 degrees, cannot be used in this case. Hence, the values for T2 and T1 will now change. But based from our situation and the given figure for the situation, whatever the values for these two tension forces are, their resultant will still be 5,000 pounds. And the angle of T1 from the resultant will still be 30 degrees. Now, the angle of T2 from the resultant will be set back to alpha. Lastly is this angle, which let's say is beta. We can solve for beta in terms of alpha because we know that the angles 30 plus alpha plus beta is equal to 180 degrees. Still, the sum of the angles of a triangle. Beta now would be equal to 150 minus alpha. At this point, we have an oblique triangle with values for its one side and one angle, but the other two angles are in terms of alpha. Therefore, we can use the sine law. If we will choose the sides R and T2, by sine law, we will have R being 5,000 over the sine of the opposite angle, which is 150 minus alpha, equals T2 over the sine of the opposite angle, 30. We can multiply both sides of the equation by sine 30, which will cancel the sine 30 at the right term where T2 is, leaving us with T2 being equal to 5,000 times sine 30. This is the sine 30 I just multiplied at the left term and brought up at the numerator, over sine 150 minus alpha. We can still simplify this equation by solving 5,000 sine 30 at the numerator, which is just 2,500 over sine 150 minus alpha. And this is the equation for the tension in rope 2, which is T2 in terms of alpha. Now that we have this equation, we can then apply the principle of maxima and minima from calculus. That is, the derivative of T2 with respect to alpha must be set or equal to 0. Since the equation for T2 is a ratio of two differentiable functions, we can then apply the quotient rule. If we will let the numerator, which is 2,500, as u, and the denominator, which is sine of 150 minus alpha, as v, using the given rule, first, we must copy v, which is the denominator being sine of 150 minus alpha, times the derivative of u, which is our numerator being a constant. The derivative of a constant is always equal to 0. Therefore, we will have times 0 minus copy u, which is our numerator being 2,500, times the derivative of v, which is a sine function. The derivative of a sine function is the cosine of the same function. Therefore, we will have times cosine of 150 minus alpha. Notice that we have a function inside our cosine function, which is the 150 minus alpha. Therefore, we must apply the chain rule, which states that we must multiply the function inside to our original cosine function. Doing so, the derivative of 150, which is a constant, is 0. The derivative of negative alpha with respect to alpha is negative 1. Hence, the derivative of the function inside is simply negative 1. All of these over the square of v, which is our denominator. Therefore, we will have the square of sine 150 minus alpha. Then, we will set all of these equal to 0. Notice that we can cancel out the first term at our numerator because the sign of 150 minus alpha is multiplied to 0. If we will multiply both sides of the equation by the denominator, which is the square of sine 150 minus alpha, we can then cancel that out and still leave us a 0 at the right term because the denominator will also be multiplied to 0. Similarly, we can also do what we just did at the 2,500 attached at the second term of our numerator. Hence, we can also cancel the 2,500, leaving us only with these. From what's left, we can still simplify it because the negative of negative 1 is simply positive 1. Hence, leaving us with cosine of 150 minus alpha is equal to 0. Solving now for alpha will give you a value equal to 60 degrees. And this is the final answer for the second or last question. For this question, there's actually a much easier and shorter way of solving what is being asked. Let us take the resultant R and represent it as this white solid line, which we knew and discussed a while ago that no matter what the values for T2 and T1 are, the value for their resultant will not change, being still 5,000 pounds, including also the angle of T1 from the resultant, which is the 30 degrees. Let us look at the possible orientations of T2 represented as the faded white broken lines. T1, on the other hand, is represented as the white dotted line. As T2 changes, so as its angle from the resultant being alpha, which we are solving in this question. Since the angle of T1 from the resultant will also not change, being 30 degrees, therefore T1 will either shorten or extend as observed a while ago depending on T2. By inspecting the developed figure, we can observe that the shortest possible faded white broken line is the one perpendicular to the white dotted line, creating an angle of 90 degrees. With this in mind, therefore, T2 is minimum if its length is the shortest, and T2's length is shortest when it is perpendicular to T1. Therefore, the angle between T2 and T1, which is 150 minus alpha, must be equated to 90 degrees. Solving now for alpha will give you a value equal to 60 degrees, which is still the answer for this question. And here ends our video. Thank you for watching.